The Vehixcare platform processes erratic, highly spiky telemetry data, calculates driver behavior scores, and triggers real-time geofence alerts for thousands of vehicles simultaneously. When deploying applications at this scale, infrastructure teams often debate whether to rely on Terraform or Kubernetes as their primary deployment tool. That debate overlooks a critical distinction. Terraform manages the cloud control plane. Kubernetes manages the application data plane. This diagram splits the responsibilities. On the left, the cloud control plane consists of static, billing-attached Azure resources. If a resource appears on your monthly Microsoft invoice, like a virtual network or a database account, Terraform provisions it. On the right, the application data plane contains the transient, ephemeral workloads operating inside the cluster. These are the pods, routing rules, and background processors that do the actual computing. We're going to construct this architecture layer by layer to see exactly how these two distinct systems hand off responsibilities to enable zero downtime scaling. Conflating these two planes results in fragile systems. Enforcing a strict boundary between them is a prerequisite for multi-region resilience. We start with an empty Azure region. Terraform initiates the build by evaluating its dependency graph, determining the exact order in which to create resources. Terraform establishes the stateful foundation. It does this while remaining completely blind to the .NET applications or telemetry services that will eventually run there. Here we see an isometric grid representing the initial network provisioning. Terraform assigns isolated, non-overlapping subnets from the 10.0.0.0/8 CIDR address space. At the perimeter, an application gateway with a web application firewall filters external traffic. Inside those subnets, Terraform creates the Azure Kubernetes service nodes, locking system and user node pools into the architecture. Tracking all of this creates a vulnerability. Terraform maps these real-world Azure resources to a state file, and if multiple team members run deployments concurrently, that file will corrupt. To prevent this, the state file is secured inside a separate Azure storage account, which enforces blob leases to lock the file and block concurrent modifications. Moving to the data layer, Terraform provisions the database backbone, a Cosmos DB account configured to use the MongoDB wire protocol. To handle severe spikes in GPS telemetry ingestion, this database is configured with an autoscale setting of 40,000 request units per second. For multi-region resilience, Terraform configures automatic failover routing, establishing West Europe as the primary database, with North Europe acting as the immediate secondary. The exact moment the Terraform apply command finishes, its job is done. It holds no awareness of application health, of API latency, or pod crashes. We now move from the static infrastructure layer into the dynamic Kubernetes cluster, which manages the ephemeral life cycles of the actual workloads. The core workload here is the telemetry API. Kubernetes distributes this application across a baseline of 3 replica pods, scaling up to a maximum of 20. By default, Kubernetes scales based on CPU utilization. For high-velocity data ingestion, CPU reaction times are often too slow. The solution is configuring the Horizontal Pod Autoscaler, or HPA, to read custom metrics directly from Prometheus. This chart tracks the exact trigger. The HPA evaluates incoming traffic, and the moment telemetry messages exceed 1,000 per second, it bypasses CPU limits and immediately increases the pod count. Updating this API carries significant risk. Pushing a new container image while the system is actively ingesting live vehicle data normally results in dropped packets. Kubernetes handles this through a precise rolling update strategy designed to maintain active connections. The deployment is configured with a max surge 1 parameter. This forces the cluster to fully spin up and verify a new pod before it touches an old one. Paired with a max unavailable 0 parameter, the cluster ensures that total compute capacity never dips below the required threshold during the entire deployment cycle. Kubernetes treats the static Azure infrastructure purely as a host resource, autonomously manipulating pod replicas to absorb unpredictable user demand. Beyond synchronous APIs, the cluster also routes continuous asynchronous event streams. These streams feed into background processors running rx.net pipelines, which calculate complex driver behavior scores in real time. To manage application-level backpressure, rx.net utilizes bounded queues, capped precisely at 10,000 capacity. This event funnel illustrates the buffer window. By configuring a 5-second holding period, the processor safely absorbs sudden bursts of traffic, preventing the system from experiencing memory leaks. To scale these background processors, the architecture introduces Kubernetes Event-Driven Autoscaling, or KEDA. It bypasses standard metrics. As the Azure Service Bus queue depth fills up, KEDA reads that volume and spins up additional processor pods to match the backlog. Once processed, this data moves to the client-facing layer, where Signal R hubs manage real-time communication back to the users. The primary failure risk at this layer is connection stability. Thousands of fleet dashboards rely on persistent WebSockets, which will drop if the underlying pods churn or scale down. The network-level solution targets the Azure load balancer, configuring it with a specific parameter, session affinity client IP. This is paired with a 10,800-second timeout, tethering a user's WebSocket connection securely to a specific pod for the duration of a long tracking session. Without aligning KEDA's event scaling and Signal R's session affinity, spiky data bursts would silently overwhelm individual pods and sever live client connections across the platform. The most critical intersection point between the static infrastructure state and the dynamic cluster workloads is secret management. Terraform's distinct responsibility here is provisioning a highly secure, hardware security module-backed Azure Key Vault. During infrastructure creation, Terraform generates the Cosmos DB connection strings and the JWT signing keys, outputting them directly into this vault. Kubernetes takes over from there. It utilizes the Secret Store CSI driver to securely mount these external secrets directly into the pods as readable file volumes. The most important parameter here is setting the CSI driver's poll interval to exactly 5 minutes. Every 5 minutes, the driver checks for updates. When a critical cryptographic key is rotated in the vault, the new key pushes into the pod automatically. No pod restart or CI/CD redeployment is necessary. This integration eliminates secret rotation downtime. It takes a high-risk maintenance event and turns it into an invisible background process. This comparison outlines the real-world results of this integrated architecture. By utilizing Kubernetes rolling updates, deployment speed dropped from 12-minute maintenance windows down to just 45 seconds. Infrastructure throughput saw a 5 times increase, allowing the platform to process 25,000 telemetry messages every second. Because the cluster scales down dynamically during off-peak hours, monthly Azure compute costs were reduced by 31%. On the resilience front, Cosmos DB automatic failovers now complete in just 3 minutes. During those failovers, Kubernetes liveness probes automatically catch any pods that drop their database connections and instantly restart them. The operational split is clear. Terraform provisions exactly what Azure bills for. Kubernetes dynamically runs exactly what the customers interact with. Strictly enforcing this architectural boundary results in a platform that maintains its own health and scales to match the exact requirements of the fleet.